Gigantism is often portrayed as nature's ultimate solution. Bigger bodies dominate landscapes. Height grants access to food beyond reach. Mass deters attack. In popular imagination, size itself becomes survival. But in evolution, nothing is free. For every advantage gained through scale, a cost is imposed elsewhere, in energy, in physiology, in flexibility, and in time. The largest animals to ever walk on land did not simply grow larger because they could. They did so because, for a brief window in Earth's history, the world allowed it. And when that world changed, size became a liability. This documentary explores that cost through one of the most extreme examples of terrestrial gigantism ever known, Brachiosaurus. At first glance, Brachiosaurus appears to embody evolutionary success. Towering above its environment, it fed where few others could. Its sheer height lifted its head beyond the reach of most predators. Its mass transformed danger into inconvenience. In its prime, an adult Brachiosaurus would have been nearly untouchable. Yet beneath this apparent dominance lay a fragile balance. To sustain a body of such scale required continuous intake of food, precise physiological regulation, and an ecosystem capable of supporting enormous energy demands without interruption. Unlike smaller animals, Brachiosaurus could not afford prolonged scarcity. It could not rapidly relocate. It could not adapt its diet quickly. It could not shrink. Its survival depended not on strength, but on stability. The world of the late Jurassic provided that stability for a time. Warm global temperatures, high atmospheric carbon dioxide, and extensive plant growth created conditions uniquely suited to giant herbivores. Forests grew tall and dense, productivity was high, seasonal extremes were muted. In this environment, gigantism paid off. But evolutionary success is measured not by dominance at a moment, but by resilience across change. As environments fluctuate, the very traits that once provided advantage can impose constraint. Large bodies require time to grow. They require years before reproduction is possible. Their populations recover slowly from loss. Their energy needs remain constant even as resources decline. Gigantism reduces risk from predators, but increases exposure to ecological stress. This distinction is critical. Brachiosaurus did not live under constant threat of being hunted. Its size protected it from direct predation once adulthood was reached. The danger it faced was slower, quieter, and far more difficult to evade. It was the danger of dependency. A dependency on towering vegetation, a dependency on stable water availability, a dependency on climate remaining within narrow bounds. Where smaller animals could adapt through speed, diversity of diet, or rapid reproduction, Brachiosaurus was committed to a single strategy, one that required the world itself to cooperate. That cooperation did not last forever. This film does not ask how big Brachiosaurus was, nor does it attempt to crown it as the largest or strongest of its kind. Instead, it asks a different question, one far more revealing. What did it cost to be a giant? What physiological burdens did such size impose? How much energy was required simply to remain alive? What risks came with slow movement and delayed reproduction? And why did gigantism, once so successful, ultimately disappear from terrestrial ecosystems? By examining Brachiosaurus not as a marvel of size, but as a system under constant demand, we begin to see gigantism not as an evolutionary endpoint, but as a narrow path, one that can be followed only under precise conditions. This is the story of how size became survival and how survival became constraint. To understand that cost, we must first understand the world that made giants possible. Brachiosaurus did not arise in isolation. Its size was not an anomaly produced by chance, nor was it the inevitable outcome of evolutionary ambition. It emerged within a specific set of environmental conditions, conditions that existed only briefly in Earth's long history. To understand why gigantism was possible at all, we must first understand the world that sustained it. The late Jurassic was a time of relative climatic stability. Global temperatures were warmer than today, with little evidence for permanent polar ice. Seasonal extremes were muted, reducing the frequency of prolonged cold or drought. For large herbivores, this stability mattered more than temperature alone. It meant predictability. Atmospheric carbon dioxide levels were significantly higher than modern values. Elevated CO2 altered plant physiology, increasing growth rates and enabling the expansion of large woody vegetation. Forests were extensive and productive, forming continuous landscapes rather than fragmented patches. This abundance of plant matter created the foundation upon which giant herbivores could exist. Importantly, the vegetation of the late Jurassic differed from modern ecosystems. Flowering plants had not yet diversified. Instead, forests were dominated by conifers, cycads, ginkgos, and ferns. Many of these plants grew tall and produced large amounts of relatively low nutrient foliage. This combination favored herbivores capable of processing vast quantities of plant material rather than selecting high-quality food. Brachiosaurus was uniquely suited to exploit this environment. Its elevated feeding posture allowed it to access foliage well above ground level, reducing competition with other large herbivores. While sauropods such as Diplodocus and Apatosaurus focused on low to mid-level vegetation, Brachiosaurus occupied the upper canopy. This vertical separation of feeding niches is a critical factor, often overlooked. In ecosystems with multiple giant herbivores, competition is not eliminated by size alone. It is reduced through specialization. Brachiosaurus did not simply eat more than others, it ate differently. The geography of the late Jurassic further supported gigantism. Continental configurations created broad, low-lying regions with extensive river systems and floodplains. These environments supported dense plant growth and reliable water sources. For a massive animal with limited mobility, access to water was non-negotiable. Water availability did more than sustain hydration. It moderated temperature, supported vegetation, and reduced mechanical stress during movement. For animals weighing tens of tons, even small reductions in effective body weight, such as those provided by soft, water-rich substrates, could reduce energetic costs. Crucially, this world did not demand speed. Predator pressure existed, but it did not require rapid escape from frequent attacks. Large theropods were present, but their hunting strategies were constrained by the risks involved in attacking enormous prey. For adult Brachiosaurus, predation was a rare event rather than a constant threat. This ecological context altered the balance of survival strategies. Where smaller animals relied on speed, agility, or concealment, Brachiosaurus relied on mass and height. In an environment that did not penalize slowness, gigantism became viable. The stability of plant communities also played a decisive role. Large herbivores cannot tolerate frequent collapse of food sources. Their populations depend on long-term continuity. The late Jurassic provided this continuity through relatively stable climate regimes and expansive vegetation zones. However, this stability came at a cost: rigidity. The very factors that allowed gigantism also reduced ecological flexibility. When environments remain stable for extended periods, specialization increases. Organisms become finely tuned to existing conditions and less capable of rapid adjustment. Brachiosaurus exemplifies this trade-off. Its anatomy reflects commitment rather than compromise.
Long forelimbs, a high shoulder posture, and a vertically oriented neck all indicate a feeding strategy optimized for a specific ecological role. This specialization worked extraordinarily well as long as the environment remained cooperative. The fossil record suggests that sauropods flourished across multiple regions during this time, indicating that the conditions supporting giantism were not local anomalies. They were global patterns. But global patterns, too, are temporary. Changes in climate, tectonics, and plant communities gradually altered these landscapes. As conditions shifted, the advantages conferred by extreme size began to erode. What once allowed giants to thrive would eventually constrain them. Understanding this world is essential to understanding the cost of giantism. Size alone did not define Brachiosaurus's success. Its success was conditional, dependent on a rare alignment of climate, vegetation, geography, and ecological structure. In the next part, we will examine how Brachiosaurus was physically built to exploit this world, and how the very architecture that made it successful also imposed limits that could not be easily escaped. The body of Brachiosaurus was not simply enlarged, it was reorganized. Every aspect of its anatomy reflects the demands of supporting extreme size while remaining functional within the limits imposed by gravity, biology, and energy. Giantism, in this case, was not achieved by scaling up a typical dinosaur body plan, but by reshaping it into something highly specialized. At the core of this design was posture. Unlike many other sauropods, Brachiosaurus possessed forelimbs that were longer than its hind limbs. This unusual proportion elevated the front of the body, creating a steeply sloping back and a naturally high feeding position. The result was an animal whose head was carried far above the ground, even without raising its neck. This posture fundamentally changed how Brachiosaurus interacted with its environment. While other sauropods fed primarily at low or intermediate heights, Brachiosaurus accessed vegetation several meters above the reach of its contemporaries. This was not merely an advantage, it was a structural commitment to a specific ecological role. The neck, often the most visually striking feature, was both an asset and a burden. Its length allowed access to high foliage without constant movement of the entire body, reducing the energetic cost of locomotion. However, a long neck introduces mechanical challenges. Every additional meter increases leverage forces, demands muscular support, and complicates blood circulation. To manage these forces, the vertebrae of Brachiosaurus were extensively pneumatized.
Air-filled spaces reduced bone mass without sacrificing strength. This adaptation lightened the neck and torso, lowering the overall energetic cost of supporting such a large structure. Pneumatization was not unique to Brachiosaurus, but its scale was extreme. The rib cage and torso housed a massive digestive system. For an herbivore consuming large quantities of low-nutrient plant material, digestion was a slow, continuous process. Food needed time to break down, and volume mattered more than selectivity. The body of Brachiosaurus reflects this reality. It was built to process bulk. This dietary strategy further constrained movement. A full gut added weight and inertia. Rapid acceleration or sudden directional changes would have been inefficient and potentially destabilizing. Speed was never the goal, stability was. The limbs of Brachiosaurus were engineered for load-bearing, not agility. Thick columnar bones transmitted weight directly downward, minimizing bending stress. Joints were structured to limit lateral movement, reducing the risk of collapse under immense loads. This design allowed Brachiosaurus to stand and move reliably, but at the expense of flexibility. Such limbs function best on firm, predictable ground. Uneven terrain, steep slopes, or soft substrates would have posed challenges. While Brachiosaurus likely navigated floodplains and open forests effectively, it was not built for rugged landscapes. Its architecture favored environments that did not demand frequent maneuvering. The tail, often overshadowed by the neck, played a crucial role in balance. Acting as a counterweight, it helped stabilize the body and manage shifts in center of mass. However, unlike some other sauropods, the tail of Brachiosaurus was not especially elongated or whip-like. Its role was primarily supportive rather than defensive. Taken together, these features reveal an animal optimized for a narrow range of conditions. The architecture of gigantism is not versatile. It is efficient within specific boundaries and unforgiving outside them. Every structural solution introduces a corresponding constraint. This is the defining paradox of Brachiosaurus. The same anatomical traits that allowed it to thrive in the late Jurassic world also limited its ability to respond to change. Long limbs and a high feeding posture reduced competition, but they also tied survival to the continued presence of tall vegetation. A massive digestive system allowed bulk feeding, but demanded constant intake. Columnar limbs provided stability, but reduced adaptability. Importantly, none of these traits are flaws. They are successful solutions to a particular ecological problem. But success in evolution is contextual. What works exceptionally well under one set of conditions may fail when those conditions shift. The architecture of Brachiosaurus reflects commitment rather than compromise. Once such a body plan evolves, retreat becomes difficult. Reducing size, altering posture, or changing diet would require fundamental restructuring across generations. Evolution does not reverse easily. This irreversibility is a critical aspect of the cost of gigantism. Large size locks lineages into specific ecological pathways. Flexibility is traded for efficiency. Resilience to predators is traded for vulnerability to environmental change. As long as the late Jurassic world remained stable, this architecture functioned. Brachiosaurus was not struggling to survive, it was thriving. But stability is temporary. When conditions begin to shift, specialization becomes a liability. In the next part, the focus will turn inward, away from bones and posture, and toward the physiological systems that kept such a massive body alive. It is here, in the demands placed on the heart, circulation, and metabolism, that the true cost of giantism becomes impossible to ignore. The most profound cost of giantism is not visible in bone or posture. It lies within the living systems that must operate continuously to keep an enormous body alive. For Brachiosaurus, survival depended on physiology pushed close to its limits. At the center of this challenge was circulation. With its head held many meters above the heart, Brachiosaurus faced a problem unmatched by any living land animal. Blood had to be delivered upward against gravity to supply the brain with oxygen and nutrients. The greater the vertical distance, the greater the pressure required. This is not a trivial scaling issue. It is a fundamental constraint imposed by physics. Modern giraffes offer a useful comparison, though only up to a point. Giraffes possess specialized cardiovascular adaptations, including high blood pressure and reinforced blood vessels to supply the brain while preventing damage when the head is lowered. Even so, they operate near physiological limits. Brachiosaurus would have exceeded those limits by a wide margin. To maintain adequate cerebral blood flow, its heart would have needed to generate exceptionally high pressures. This raises immediate questions. How large was the heart? How powerful? Could a single heart sustain such pressure without structural failure? These questions remain debated precisely because soft tissues are not preserved in the fossil record. Some hypotheses propose an enormous, highly muscular heart capable of producing sufficient pressure. Others suggest additional anatomical features, such as auxiliary pumps or specialized valves, to reduce the effective pressure gradient. None of these proposals can be confirmed directly. What can be stated with confidence is that circulation in Brachiosaurus required extraordinary solutions. Blood pressure, however, is only part of the equation. High pressure increases the risk of vascular damage. Capillaries in the brain are delicate. Excessive pressure can cause rupture, edema, or impaired function. Any viable system must therefore balance delivery with protection. This balancing act would have constrained behavior. Rapid changes in head position could have posed serious risks. Sudden lowering of the head might lead to dangerous pressure spikes, while rapid elevation could momentarily deprive the brain of blood. Such risks suggest that Brachiosaurus may have moved its neck deliberately, avoiding abrupt vertical motion. Respiration presented another challenge. A massive body requires continuous oxygen delivery, yet lung tissue must be protected from collapse under pressure. Many sauropods, including Brachiosaurus, likely possessed extensive air sac systems similar to those of modern birds. These systems would have improved oxygen exchange efficiency while reducing body mass. Air sacs also help regulate heat, an important consideration for a large animal in a warm climate. However, effective cooling requires airflow. A slow-moving animal with a high metabolic demand faces a constant struggle to dissipate excess heat. Water access and shade would have been essential. Metabolism itself is another unresolved issue. Whether sauropods were fully endothermic, ectothermic, or occupied an intermediate state remains debated.
What is clear is that sheer size alters thermal dynamics. Large bodies retain heat efficiently. This can be advantageous in cool environments, but problematic in warm ones. If Brachiosaurus generated significant internal heat, managing that heat would have been critical. Excessive body temperature can impair enzyme function, disrupt neural activity, and reduce overall performance. Once again, stability is key. Extreme size narrows the range of tolerable conditions. Digestion added further complexity. Processing enormous quantities of plant material requires time. A large gut slows movement and increases inertia. But slowing digestion is not an option. Energy demand remains constant. The system must operate without interruption. Any prolonged disruption, reduced food intake, illness, injury would have cascading effects. Smaller animals can compensate through reduced activity or metabolic downregulation. For Brachiosaurus, margins were thinner. The system depended on continuous throughput. This dependence creates vulnerability. Not vulnerability to predators, but to physiological stress. Injury to a limb, impairment of digestion, or disruption of circulation could quickly become fatal, not because the animal was weak, but because recovery options were limited. Even sleep may have posed challenges. Rest is essential, yet lying down and standing up would have required careful control to avoid injury or circulatory shock. While sauropods clearly managed these behaviors successfully, the energetic and mechanical costs would have been high. Taken together, these physiological demands reveal the true cost of gigantism. Brachiosaurus was not simply large, it was finely balanced. Every system, cardiovascular, respiratory, digestive, thermoregulatory, operated close to its effective limits. This does not imply fragility in a daily sense. Brachiosaurus was robust within its ecological context. But robustness is not the same as resilience. Robust systems function well under expected conditions. Resilient systems tolerate disruption. Gigantism favors robustness at the expense of resilience. This distinction explains why extreme size can persist for millions of years and then disappear. As long as environmental conditions remain within narrow bounds, the system holds. When those bounds are exceeded, failure becomes more likely. The physiological cost of gigantism therefore lies not in constant struggle, but in reduced tolerance for change. Brachiosaurus thrived in a stable world. It paid for that success by binding its survival to that stability. In the next part, attention will turn to energy itself, the continuous demand for food, and the consequences of relying on bulk feeding in a world that does not always provide without interruption. For an animal of Brachiosaurus's size, survival was governed less by danger than by arithmetic. Every day required a balance between energy gained and energy spent. Miss that balance for too long, and even the largest body becomes unsustainable. Gigantism does not reduce energy needs, it transforms them. While large animals are more energy efficient per unit of body mass than small ones, their absolute demands are enormous. Brachiosaurus did not need to eat slightly more than its contemporaries. It needed to eat vastly more, every single day, without interruption. Hunger was not an occasional state. Feeding was a constant obligation. The plants available in the late Jurassic were abundant, but they were not nutrient-rich. Conifers, cycads, and other dominant plant groups offered large quantities of fibrous material with relatively low caloric density. For Brachiosaurus, selectivity was less important than volume. The strategy was simple: eat continuously, process slowly, and extract what energy was available over time. This approach shaped behavior. Brachiosaurus could not afford long periods without feeding. It likely spent much of its waking life browsing, moving slowly between stands of vegetation. Long-distance travel would have been costly, not because it was impossible, but because it interrupted intake. Movement had to be efficient, deliberate, and justified. Its elevated feeding posture reduced competition. By focusing on high foliage, Brachiosaurus avoided direct overlap with other large herbivores feeding at lower levels. This vertical niche partitioning reduced conflict, but it also narrowed dietary options. If tall vegetation declined, alternatives were limited. Unlike smaller herbivores, Brachiosaurus could not rapidly switch to different plant types. Its neck, posture, and feeding mechanics were optimized for a specific resource. While it could likely consume a range of plant species, they needed to be accessible at height and available in large quantities. Water access was inseparable from feeding. Digesting massive volumes of plant material requires hydration. Rivers, floodplains, and water-rich environments were not optional components of Brachiosaurus's range. Any disruption to water availability would have compounded the challenge of meeting energy demands. Feeding itself imposed physical constraints. A full digestive tract added substantial weight. This increased inertia and reduced maneuverability. The act of eating made movement more difficult, yet movement was necessary to reach new food sources. The animal existed in a constant trade-off between intake and locomotion. Importantly, this system left little margin for error. Short-term shortages might be tolerable, but prolonged scarcity would have cascading effects. Reduced intake leads to reduced energy for digestion, thermoregulation, and immune function. Recovery would be slow because regaining lost mass requires time and sustained abundance. Smaller animals can compensate for scarcity through behavioral flexibility. They can enter torpor, migrate rapidly, or shift diets. Brachiosaurus had fewer options. Its size limited speed. Its specialization limited dietary flexibility. Its growth strategy limited reproductive buffering. This does not imply that Brachiosaurus lived on the edge of starvation. On the contrary, the late Jurassic world appears to have supported its needs for millions of years. The point is that food was insufficient, but that the cost of failure was high. Energy demand also influenced population structure. Large herbivores tend to exist at low densities. Even in productive environments, only a limited number of individuals can be supported. This means that population recovery from loss is inherently slow. Birth rates must offset mortality over long timescales. In such systems, stability matters more than abundance. A brief period of reduced productivity may have little impact on small, fast-breeding animals. For a giant herbivore, the same disruption can echo for generations. Feeding behavior likely reflected this reality. Brachiosaurus may have followed predictable routes through its environment, returning to areas after vegetation had time to recover. Such patterns reduce overexploitation, but increase dependence on landscape continuity. Fragmentation would have been costly. There is also the question of digestion time. Large herbivores benefit from long retention times, allowing microbial fermentation to extract maximum energy from fibrous plants. But long retention means delayed response. If food quality declines, the digestive system cannot adjust instantly. The effects are felt later, when options may already be limited. This lag further reduces resilience. Energy balance is maintained not moment to moment, but over extended periods. Disruptions accumulate before becoming visible, and by the time they do, reversal may be difficult. The constant demand for energy defines the daily life of a giant. It shapes movement, habitat choice, social structure, and vulnerability. It also explains why giantism is rare and transient in evolutionary history. Brachiosaurus succeeded because the world it inhabited could meet its demands. When that world began to change through shifts in climate, vegetation, or hydrology, the cost of size increased. The same energy strategy that once conferred advantage became a constraint. Crucially, this does not require catastrophic famine. It requires only a reduction in predictability. A system that depends on continuous throughput cannot tolerate sustained irregularity. The cost of gigantism, in energetic terms, is not hunger itself. It is dependence. Dependence on abundance, on stability, and on uninterrupted access to resources. In the next part, we will examine how slowness, often misunderstood as weakness, actually functioned as protection, and why the real danger to Brachiosaurus did not come from predators, but from the limits imposed by its own scale. Slowness is often framed as a flaw. In modern ecosystems, speed is associated with survival, escape, and adaptability. From this perspective, an animal as massive and slow-moving as Brachiosaurus appears vulnerable by definition. Yet this assumption collapses when examined in ecological context. For Brachiosaurus, slowness was not a weakness. It was a consequence, and in many ways, a form of protection. Predation pressure in the late Jurassic did not operate uniformly across all body sizes. Large theropod predators, such as Allosaurus and Torvosaurus, were formidable hunters, but they were constrained by risk. Attacking a fully grown sauropod weighing tens of tons was not merely difficult, it was potentially fatal. One misjudged strike could result in crushed bones, internal injury, or immobilization. For a predator dependent on mobility to hunt and feed, such injury would likely be a death sentence. As a result, the cost-benefit calculation of attacking an adult Brachiosaurus was overwhelmingly unfavorable. This dynamic mirrors patterns seen in modern ecosystems. Elephants, rhinoceroses, and large bovines are rarely targeted by predators, not because predators lack aggression, but because the risk is too high. Predators focus instead on juveniles, the injured or the isolated. There is no fossil evidence indicating systematic predation on healthy adult Brachiosaurus. No bite marks consistent with lethal attacks, no accumulations suggesting repeated kills, and no anatomical adaptations in predators that clearly indicate specialization for such prey. Absence of evidence is not proof of absence, but the pattern is telling. Slowness in this context did not equate to vulnerability. It equated to inevitability. An adult Brachiosaurus did not need to flee. Its presence alone altered predator behavior. Risk avoidance, not pursuit, defined the interaction. This does not mean predation played no role at all. Juveniles would have been at risk. Newly hatched individuals, small and lightly built, lacked the mass-based protection of adults. Mortality at early life stages was likely high, a common pattern among large animals that produce many offspring. However, once a Brachiosaurus reached sufficient size, the balance shifted decisively. Survival probability increased dramatically. Slowness no longer mattered because speed was no longer required. This distinction is essential. Slowness becomes a problem only when escape is necessary. For Brachiosaurus, escape from predators was rarely necessary after maturity. The threat it faced was not sudden, but cumulative. Environmental change does not chase. It advances slowly and relentlessly. Slowness limited Brachiosaurus's ability to respond to such change. When food distribution shifted, when water sources moved, or when vegetation patterns altered, rapid relocation was not an option. Movement was possible, but it was costly and slow. Long-distance migration would have required enormous energy investment and time. This meant that Brachiosaurus depended heavily on local environmental continuity. If conditions degraded gradually, the animal could not simply outrun the problem, it had to endure it. In this sense, slowness functioned as a double-edged trait. It was harmless, even advantageous in the face of predators, but restrictive in the face of ecological instability. The danger was not teeth or claws, but delay.
Delay in reaching new resources. Delay in responding to drought. Delay in population recovery. Each delay increased risk. The myth that Brachiosaurus was doomed by predators arises from a misunderstanding of scale. Predators shape ecosystems, but they do not operate independently of physics. There are limits to what even the largest hunters can attempt. Gigantism exploited those limits effectively. By reducing predation risk, gigantism allowed Brachiosaurus to invest less in speed, armor, or aggressive defense. Energy could instead be allocated to growth and maintenance. This trade-off worked as long as environmental conditions remained favorable. But it also removed a form of selective pressure that maintains flexibility. In smaller animals, predation enforces responsiveness. It favors agility, vigilance, and adaptability. In giants, the absence of predation shifts the selective landscape. What replaces predation as the primary constraint is environment itself. Slowness amplified exposure to that constraint. It reduced the capacity to track shifting resources and to exploit transient opportunities. It also limited the ability to escape deteriorating habitats. Importantly, this does not imply that Brachiosaurus was poorly adapted. It was exquisitely adapted to a specific set of conditions. Slowness was not accidental. It was the product of optimizing for mass, stability, and energy efficiency. The cost emerged only when conditions changed. This perspective reframes the narrative of survival. Brachiosaurus was not outcompeted by predators. It was not hunted into extinction. Its decline, whatever the precise mechanisms, would have been driven by environmental factors that its size made difficult to accommodate. In evolutionary terms, slowness was not selected against because it did not need to be. The selective pressure that ultimately mattered
was not predation, but variability. Gigantism performs best in worlds that change slowly. When change accelerates, the same traits that once conferred dominance become constraints.
Slowness, therefore, is best understood not as a flaw, but as a signal that the organism is operating at a scale where different rules apply. For Brachiosaurus, those rules minimized immediate danger, but maximized long-term dependence. In the next part, attention will turn to reproduction and population dynamics, the quiet processes that determine whether a lineage persists or collapses when challenged by change. For animals of extreme size, survival is not determined solely by the fates of individuals. It is determined by populations, by how quickly numbers can grow, recover, and persist through periods of stress. In this respect, gigantism carries a cost that is easy to overlook because it operates slowly and invisibly. Brachiosaurus was protected by size as an adult, but it began life at a severe disadvantage. Like all non-avian dinosaurs, Brachiosaurus reproduced by laying eggs. These eggs were small relative to adult body size, constrained by biological limits on egg structure and incubation. No matter how large the adult became, the offspring began life vulnerable, lightly built, and exposed. This reproductive strategy creates a steep survival curve. Mortality is highest early in life and declines dramatically only after sufficient growth has been achieved. For Brachiosaurus, the gap between hatching and safety would have been measured in years. During this period, juveniles faced multiple threats. Predators capable of ignoring adult Brachiosaurus would have readily targeted smaller individuals. Environmental hazards, flooding, drought, heat stress would have taken additional tolls. Even minor injuries could prove fatal at small sizes. To offset these losses, Brachiosaurus likely relied on numbers. Producing many eggs increases the probability that some offspring will survive to adulthood. This is a common strategy among large animals with limited parental care. But it introduces a new risk. Population turnover becomes slow. Large animals take time to grow. Years pass before reproduction is possible. Even under ideal conditions, generations overlap slowly. This means that population recovery after decline is inherently delayed. Losses cannot be replaced quickly. In stable environments, this is not a problem. Low mortality combined with long lifespan can maintain population balance. But when conditions deteriorate, slow reproduction becomes a liability. If food availability declines, juvenile survival drops first. If drought persists, fewer individuals reach maturity. Adults may survive for some time, masking population decline. By the time the effects become visible, recovery may no longer be possible. This lag is a critical aspect of population risk. It creates the illusion of stability even as the system moves toward collapse. In such scenarios, extinction does not arrive suddenly. It unfolds quietly across generations. The fossil record offers only limited insight into the reproductive behavior of Brachiosaurus. No nests or eggs have been definitively attributed to the species. However, comparisons with other sauropods suggest similar strategies: widespread egg-laying, minimal parental care, and reliance on environmental conditions to protect offspring. This strategy works best when environments are predictable. Floodplains and stable climates can provide suitable nesting grounds year after year, but unpredictability undermines it.
Changes in rainfall patterns, vegetation cover, or sediment deposition can render traditional nesting sites unusable. Population density further compounds the problem. Large herbivores exist at low densities even in productive ecosystems. Space and resources limit how many individuals can coexist. As a result, populations are spread thinly across landscapes. Low density reduces competition, but it also reduces buffering capacity. A localized disturbance can remove a significant fraction of a population. Recolonization is slow because dispersal rates are limited by size and energy constraints. This vulnerability is often invisible in individual-focused narratives. An adult Brachiosaurus appears invulnerable, dominant, and stable, but populations operate under different rules. What protects individuals does not necessarily protect lineages. Reproductive output must not only replace losses, but also account for environmental variability. In rapidly changing conditions, strategies optimized for stability falter. This is one reason why extreme gigantism is rare and transient in evolutionary history. It is also why gigantism often coincides with long periods of environmental stability. When variability increases, selection favors smaller, faster reproducing animals that can adapt quickly. Large size becomes a burden. This does not imply that Brachiosaurus failed evolutionarily. It thrived for millions of years under favorable conditions, but its reproductive strategy tied its fate to those conditions. Once stability declined, the margin for error narrowed. The cost of gigantism in reproductive terms is therefore not low fertility, but delayed response. Population processes move slowly, and slow systems struggle in dynamic environments. This perspective shifts how we interpret extinction. It is tempting to search for a single cause, a predator, a catastrophe, a shortage. In reality, extinction often results from accumulated disadvantages that interact over time. For Brachiosaurus, reproduction amplified those disadvantages. High juvenile mortality, slow maturation, and low population density created a system that could not rapidly adjust. When pressures mounted, decline was gradual but difficult to reverse. Understanding this process is essential to appreciating the cost of gigantism. Size protects individuals, but it exposes populations. The very traits that make giants impressive also make them fragile at the scale that matters most. In the next part, we will examine ecological dependence, how reliance on specific habitats and resources further constrained Brachiosaurus's ability to respond to change, and why environmental stability was not merely beneficial, but essential to its survival.
For Brachiosaurus, survival was inseparable from the structure of its environment. Its immense size did not merely influence how it fed or moved, it defined the range of conditions under which it could exist at all. This dependence on a narrow set of ecological circumstances represents one of the most consequential costs of gigantism. Large herbivores interact with ecosystems differently from smaller animals. They do not simply consume resources, they require landscapes capable of sustaining continuous, large-scale energy transfer. For Brachiosaurus, this meant extensive tracts of tall vegetation, reliable water sources, and climatic stability over long periods. The feeding strategy of Brachiosaurus illustrates this dependence clearly. By specializing in high-level foliage, it reduced competition with other herbivores, but it also limited its options.
Trees and tall plants take time to grow. They are more sensitive to prolonged drought, temperature shifts, and changes in soil moisture than many low-growing plants. If canopy vegetation declined, replacement would not be rapid. This creates a structural vulnerability. A system based on slow-growing resources cannot respond quickly to disruption. Even moderate environmental stress can produce long recovery times. For an animal that depends on those resources daily, such delays are critical. Water availability compounded this dependency. Digestion of large volumes of fibrous plant material requires hydration. Thermoregulation in a massive body benefits from access to water-rich environments. Rivers, floodplains, and wetlands were therefore central to Brachiosaurus's range. These environments, however, are dynamic. River systems shift course, floodplains expand and contract. Seasonal variability influences plant growth and accessibility. In stable climates, these changes remain within tolerable bounds. When variability increases, predictability declines. Brachiosaurus was not well equipped to track such changes rapidly. Its size limited speed and endurance over long distances. Its energy demands constrained how far it could travel without sustained feeding. As a result, its ecological range was broad in space but narrow in flexibility. This contrasts sharply with smaller herbivores. Animals with lower energy demands can exploit patchy resources, move quickly between habitats, and tolerate short-term scarcity. They can adjust behaviorally to fluctuations. Brachiosaurus could not. It required continuity. Ecological dependence also influenced social structure. While direct evidence of herd behavior in Brachiosaurus is lacking, large herbivores often benefit from some degree of grouping, particularly during migration or resource tracking. However, large group sizes intensify pressure on local vegetation. Overuse becomes a risk. Managing this balance requires movement across large connected landscapes. Fragmentation, whether due to geographic barriers, climatic shifts, or vegetation changes, disrupts these patterns. When habitats become isolated, large herbivores suffer disproportionately. Another aspect of ecological dependence lies in the absence of redundancy. Smaller animals often have multiple fallback options, alternative foods, shelter types, or microhabitats. Brachiosaurus had fewer. Its anatomy and feeding mechanics were optimized for a specific role. Deviating from that role incurred cost. This specialization is not inherently negative. In stable systems, specialists can outperform generalists. But specialization increases exposure to change. The more precisely an organism is tuned to its environment, the more sensitive it becomes to deviations. The late Jurassic world provided the conditions Brachiosaurus required, but geological and climatic records indicate that such conditions did not persist indefinitely. Over time, shifts in sea level, climate, and plant communities altered the structure of terrestrial ecosystems. These changes did not need to be catastrophic to matter. Gradual drying, increased seasonality, or changes in plant composition could erode the foundations of gigantism. Reduced canopy cover, even if partial, would force Brachiosaurus to travel farther or compete more directly with other herbivores. Competition, in turn, raises energy costs. Feeding at lower levels would bring Brachiosaurus into overlap with species better suited to those niches. What was once a competitive advantage becomes a disadvantage. Ecological dependence also limits evolutionary response. Adjusting to new conditions through natural selection requires time and variation. For large animals with slow reproduction, that time may not be available. Environmental change can outpace adaptation. This mismatch between the pace of change and the pace of response is a recurring theme in the history of life. It explains why lineages that thrive for millions of years can disappear without dramatic external triggers. In the case of Brachiosaurus, extinction does not require a singular cause. It requires only that the environment gradually move outside the narrow range within which extreme size is viable. Once that threshold is crossed, decline becomes difficult to halt. The ecological dependence of Brachiosaurus therefore reframes the question of survival. It was not defeated by competitors or predators. It was constrained by the very systems that once sustained it. Gigantism ties success to landscape-scale stability. When that stability erodes, the cost of size becomes apparent. Large bodies cannot easily retreat, diversify, or adapt. They endure until endurance is no longer sufficient. This understanding prepares us for the final stages of the story. To grasp the full meaning of gigantism, we must consider its limits, not just ecological, but evolutionary. In the next part, we will examine why extreme size represents a ceiling rather than a pathway, and why the age of giants was always destined to be temporary. Gigantism may appear, at first glance, to be an open-ended strategy. If large size confers protection from predators, access to abundant resources, and dominance within an ecosystem, then it is tempting to imagine that evolution could simply continue scaling upward.
The history of life suggests otherwise. On land, size has a ceiling. Brachiosaurus approached that ceiling not because it was poorly designed, but because it was exquisitely constrained. Every increase in size magnifies underlying physical and biological limits. Beyond a certain point, the costs rise faster than the benefits. Gravity is the first and most unforgiving constraint. As body mass increases, weight scales faster than the strength of bone. Structural solutions, thicker limbs, columnar posture, lighter bone through pneumatization, can compensate only up to a point. Eventually, the margin of safety narrows. For Brachiosaurus, limb bones were already functioning near optimal load-bearing geometry. Further increases in mass would have required disproportionate changes in bone diameter, joint structure, and muscle attachment. These changes would have reduced mobility and increased energy cost, undermining the very advantages size was meant to provide. Physiology imposes a second ceiling. Circulatory systems must deliver oxygen and nutrients across greater distances as bodies grow larger. Pressure requirements increase. Failure risk increases. The cardiovascular demands discussed earlier were already extreme in Brachiosaurus. Pushing beyond them would have required fundamentally new solutions. Evolution rarely invents entirely new systems quickly. It modifies existing ones. When modification is no longer sufficient, progress stalls. In this sense, gigantism is not a continuous trajectory, but a narrow ridge. Brachiosaurus appears to have reached that ridge. Metabolism adds another layer of constraint.
Large animals benefit from lower mass-specific metabolic rates, but their total energy requirements remain immense. Food availability must scale accordingly. On land, primary productivity sets an upper bound. No matter how efficient digestion becomes, energy cannot be extracted faster than plants can grow. This is why the largest animals that have ever existed are marine, not terrestrial. Water supports body weight, reducing structural stress. Oceans provide vast, continuous food webs.
On land, such buffering does not exist. Brachiosaurus represents the extreme end of what terrestrial ecosystems could support. Its success does not imply that further scaling was possible. It implies that the limit was reached. Evolutionary ceilings are not hard walls. They are zones of diminishing returns. Traits can approach them, but each step forward yields less advantage and more cost. Eventually, selection favors stability rather than further increase. This helps explain why sauropods did not continue evolving ever larger forms indefinitely. Instead, later lineages explored variation in form, posture, and feeding strategy rather than size alone. Diversity replaced magnitude. Environmental change reinforces these limits. As climates fluctuate and ecosystems reorganize, flexibility becomes more valuable than dominance. Traits that lock organisms into narrow niches lose favor. Gigantism, once advantageous, becomes restrictive. The fossil record reflects this pattern. Extreme size appears episodically, coinciding with periods of prolonged stability and high productivity. It then recedes as conditions change. This cycle is not unique to dinosaurs. It appears repeatedly across evolutionary history. Importantly, the disappearance of extreme gigantism does not imply inferiority. It reflects shifting constraints. Evolution does not rank solutions. It tests them against circumstances. Brachiosaurus existed at a time when circumstances aligned. Its lineage exploited that alignment to the fullest extent possible. When those conditions changed, the pathway closed. This closure does not require sudden catastrophe. Gradual shifts are sufficient. Increasing seasonality, changes in plant composition, or altered hydrology can all erode the margins that gigantism depends on. Once those margins narrow beyond a threshold, selection favors smaller, more adaptable forms. In this context, extinction is not failure, it is transition. The lineage that produced Brachiosaurus did not vanish because it was flawed. It vanished because the world it was built for no longer existed.
Understanding this reframes how we interpret evolutionary success. Longevity, not size, is the more reliable measure. Traits that endure across changing conditions tend to be moderate, flexible, and resilient. Gigantism is impressive, but it is not resilient. Brachiosaurus teaches us that evolution explores extremes, but it does not remain there indefinitely. Extremes reveal possibilities and boundaries. They show us not only what life can achieve, but where it must stop. The evolutionary ceiling that constrained Brachiosaurus still operates today. No terrestrial animal has surpassed sauropods in size, despite millions of years of opportunity. The constraints remain unchanged. In the final part, we will step back from mechanics and biology to consider what this story ultimately means. Why does the rise and fall of giants matter,
And what does Brachiosaurus reveal about the balance between power, dependence, and survival in the history of life on Earth? The story of Brachiosaurus is often told as a celebration of scale. Towering height, immense mass, and apparent invulnerability dominate visual reconstructions and popular imagination. But when examined through the lens of biology rather than spectacle, a different narrative emerges, one that speaks less about dominance and more about balance. Gigantism was not an endpoint, it was a condition. Brachiosaurus did not represent the peak of dinosaur evolution, nor did it embody an inevitable trajectory toward larger and larger forms. Instead, it occupied a narrow window in Earth's history when environmental stability, resource abundance, and physiological feasibility briefly aligned. Outside that window, such size would have been unsustainable. This distinction matters. Evolution does not reward excess, it rewards fit. For millions of years, Brachiosaurus was well fitted to its world. Its size reduced predation risk. Its height opened access to food others could not reach. Its architecture supported efficient bulk feeding.
Within the late Jurassic landscape, these traits worked together to produce a stable, functioning organism. But fitness is contextual. It does not persist when conditions change faster than biology can respond. The cost of gigantism ultimately was not paid in a single moment. It was paid gradually as environmental flexibility declined and dependence increased. Each advantage carried an obligation: constant food intake, stable climate, predictable vegetation, and long-term ecological continuity. When those conditions eroded, size no longer protected, it constrained. This pattern is not unique to dinosaurs. Throughout the history of life, extreme specialization has repeatedly produced impressive forms and equally impressive vulnerabilities. The more precisely an organism is tuned to a specific set of conditions, the less tolerant it becomes of deviation. Brachiosaurus exemplifies this principle at an extraordinary scale. Its slow pace was not a failure of design. It was a consequence of optimizing for mass and stability. Its high energy demand was not inefficiency, but the price of sustaining a massive body on land. Its reproductive strategy was not careless, but a rational response to biological constraints. None of these traits were mistakes. Together, they formed a coherent system. But coherence does not guarantee resilience. Resilience requires flexibility, the ability to change behavior, diet, distribution, or reproduction rapidly in response to shifting conditions. Gigantism limits that ability. Large bodies take time to grow. Large populations recover slowly. Large systems resist change until change overwhelms them. This is why the age of giants was temporary. As the Jurassic gave way to new climatic regimes and evolving ecosystems, the balance shifted. Smaller herbivores with faster life cycles, broader diets, and greater mobility gained relative advantage. Gigantism, once successful, became increasingly costly. Importantly, this does not mean that Brachiosaurus was driven to extinction by a single cause. There is no evidence of sudden collapse, mass starvation, or targeted predation. Its decline would have been gradual, shaped by cumulative pressures that reduced viability over time. In this sense, the disappearance of Brachiosaurus is not a mystery to be solved, but a pattern to be understood. It reminds us that evolution explores extremes, but rarely remains there. Extremes reveal what is possible and what is fragile. They illuminate boundaries that are otherwise invisible. Brachiosaurus stands as one of the clearest expressions of terrestrial limits. No land animal before or since has exceeded sauropods in size. Despite millions of years of opportunity, those limits have not been surpassed. Gravity, physiology, and ecology continue to impose the same constraints. This continuity underscores an important truth. The rules governing life on land are remarkably stable, even as life itself changes. The story of Brachiosaurus therefore extends beyond dinosaurs. It offers insight into how biological systems respond to abundance and scarcity, stability and disruption. It shows that success achieved through dependence carries inherent risk. In a broader sense, gigantism serves as a cautionary example within evolution. Power derived from scale can obscure vulnerability. Dominance can mask dependence. Systems that appear invincible may in fact be finely balanced. Brachiosaurus was not undone by weakness, it was undone by limits. Understanding those limits does not diminish the animal's significance. On the contrary, it elevates it. Brachiosaurus represents one of the most ambitious experiments in terrestrial life, an experiment that succeeded brilliantly under the right conditions and faded when those conditions no longer held. Its legacy is not simply one of size, but of constraint. It teaches us that survival is not about maximizing a single trait, but about maintaining equilibrium across many.
In the end, the true cost of gigantism was not paid in blood or battle. It was paid in dependence on a world that could not remain unchanged forever. And that is why the giants walked only for a time.